I shall take up one very interesting problem. This problem, surely I will not give any assignment based on this problem in this cycle. I shall be giving the problem based on that in the next cycle. But this particular problem I will be covering now only to show you that how connected and disconnected the components and how all graph operations could be linked up to solve one problem. So now the problem is a very interesting problem. The problem is I shall have four cubes. Four cubes. I shall have four cubes, and the four cubes are colored differently. You can see that all faces are colored differently. And I shall now tell that there are four cubes and their faces are colored with four colors: red, blue, green, and white. Let us say that red, blue, green, and white. The objective is to stack these cubes in a column such that each side of the stack, each side, front side, back side, left side, and right side, each wall of the stack should be composed of of four different colors. That's the whole idea. So on every wall you should be able to see four colors: red, blue, green, and white. You should be able to see that. Okay, here there is no white. I think here in the picture it is yellow, red, yellow, green, and blue. All right, so the point is you should have, if I take the front right, I should see all the four colors. Right back, I should be able to see all four colors. Back left, I should see all four colors. Left front, I should be able to see all four colors. Naturally, this is an exhaustive search problem. Now, can you give the answer quickly? It is not exhaustive search. It's a method of orienting the cube such that you get four different colors on every face. All right, it definitely is an exhaustive search problem. So the complexity of the problem is, that it is non-deterministic polynomial problem. However, can you at least quickly tell me whether there exists a solution or it doesn't exist a solution? Let us see how we can solve this problem graph theoretically. Let me open up a cube. Just open up a cube. So when you open up the cube, you can see all the six faces like this: 1, 2, 3, 4, 5, 6. You just cut the cube and you have opened it up. Just you have opened it up. Is that all right? When you open up the cube, this is what you see, all the six faces. Now you can see that this face is always connected with this face because they make a pair of opposite faces, isn't it? They make the pair of opposite faces. They are strongly connected. There is a strong edge between this and this. Similarly, between this and this, there is a strong edge. Okay, which is not a variable edge. It is a fixed edge because it represents a pair of opposite faces. Similarly, this is the pair of opposite faces. So six faces in a cube shall have three pairs of opposite faces. Is it all right? Three faces of opposite faces. Now here, this face is colored red. This is red. This is red color. This is yellow color. This is green color. This is blue color. All right. So they similarly cube 2. Cube 2. These are the six faces of the cube 2. They are differently colored. Of course, there are four colors. Four colors. And cube 3 differently colored and four colors. Cube 4 has a differently colored and four colors. So four cubes made up of four colors. Now the problem is, if I stack them one above the other, all these four colors should be distinctly visible on all walls, on all total stack walls. Is that okay? On all four walls. All right. So let us construct the graph for each cube. Now I have told you that a pair of opposite faces shall make one edge. Because there are three pairs of opposite faces, every cube will be indicated by three edges and four colors. Four colors. Let every color represent the vertex. Therefore, it is a 4 vertex, 3 edge. 4 vertex, 3 edge. You just see what is the 4 vertex and 3 edge representation for cube 1. So cube 1 has red color, green color, blue color, yellow color, the 4 colors as vertices. All right. And you can see here there is a edge from red to red. There is a edge from red to green. And there is a edge from yellow to blue. Let us see. There is an edge from red to red. There is an edge from red to red. It is a self loop. There is an edge from red to green. There is an edge from red to green. There is an edge from blue to yellow. There is an edge from blue to yellow. That is what it is, a graph. Note the beauty. Cube 1 is a single physically connected. In graph, it is a disconnected graph. Is it all right? It's a disconnected. It has got two components. Graph wise, it has got two components. But physically, it is one connected box. And it has got a self loop. So this is the graph representation of cube 1. If you have understood how to construct the graph for cube 1, but remember, it is diagrammically represented. Immediately, you should represent it by a matrix. Okay, either A matrix or X matrix. That is why I have taken up this problem. I have not shown it explicitly because that's the algorithm part and that is your job. All right. So having constructed one matrix for cube 1, it now becomes very easy to construct the matrices for the remaining cube 2, cube 3, cube 4. So cube 2 is this. Cube 2 has one red to blue. So red to blue. And here red to yellow. Red to yellow. And here yellow to green. Yellow to green. So this is now one component graph. All right. And there are 4 vertices, 3 edges. 4 vertices and 3 edges. Here also 4 vertices and 3 edges. So cube 3 also has got 3 edges only, 4 vertices. Again, it's a disconnected graph. All right, you can see that it's a disconnected graph. Green to green is a loop, self loop. Blue to red, and blue to yellow. All right. Cube 4 is a connected graph, and cube 4 has got blue to yellow, green to red, okay, and yellow to green. All right, yellow to green. So it is a connected graph. Now I want to stack them one above the other. Therefore, what I am going to do is, because all vertices are common here, note here, I am going to do the union operation of all these 4 graphs. Okay, graph union. All right, that is the reason I have taken it. Of course, don't worry, I shall not give an assignment based on this in this cycle, but you should be listening to this very carefully because this becomes an important assignment in the next cycle. All right. So I shall do the union of all these 4 graphs. When I do the union, because all 4 vertices were in common for all these 3 graphs, the resultant graph shall have only 4 vertices, but the edges shall be 3 into 4. There shall be 12 edges, isn't it? Because 3 edges are contributed by each cube. There shall be 12 edges. All right. Now I shall indicate 12 edges, and in the next diagram, what I have done is this is the union of the graph, and here we have, let us understand the color code. This is of 1 cube. This color, blue color, is of 1 cube. Okay, 1 cube, blue color, maybe cube 1. All right, cube 1, and then this is another cube, this color. All right, this, what is this? Deep red or brick red is another color. So this is another 3 edges of another cube, and this purple, isn't it? Purple or violet? This is another cube, and black is another cube. Okay, there are four sets of colors indicating 4 cubes. Now what should I do? I want to now pile these cubes one above the other such that all four colors are present. Remember, this is such a beautiful English. Four colors should be present when I look at a face, and all the four cubes should also be present. Four cubes should be present. Four colors should be present. All right. Therefore, one, if you look at this face from the front, the back face is automatically decided. Is it okay? Isn't it? Back face is automatically decided because they are strong connected. Right? So, how many edges here I should choose, and what should be the belongingness of these edges? I should choose four edges of four different cubes, and all these four edges of four different cubes should be connecting all the four colors: red, blue, green and yellow. All four vertices should be connected, and I have got to choose four edges, and those four edges should be from four different cubes, right? That's the interesting. Let us see, can that be possible now? Can I remove? Can I extract that? Can I identify the presence of that? Therefore, all four vertices should be present, and they should be connected. They should be connected, and there should be four edges. How can this be possible? If all the four vertices should be connected and four edges should be there and four colors should be there, then it has got to be a circuit. Starting from, let us say, if I start from the red vertex, I should somehow connect the blue, connect the yellow, connect the green, and connect the red again. It must be a circuit. I have not introduced this traversal. That is the reason I introduced this topic, to tell you that in the next topic we will be discussing how to identify the existence of the circuit. But then this circuit should be composed of all four colored edges here. What I am trying to tell you is, here I have a choice. Either I can choose this purple edge or I can choose the black edge. In case I choose the purple edge here, I am surely prevented from choosing the purple edge here. Then I have the choice either to choose this or to choose this. Is it okay? All right. In case I choose a black edge here, nowhere else I can choose the black edge. Nowhere else I can choose the black edge. So I should carefully choose four edges connecting all four vertices, and all the four edges should be of different colors representing different cubes. If I can do that, I have got one wall made up of surely four different colors. By the virtue of one wall, the back wall is also automatically confirmed. Is that all right? Let's see whether I can extract one such subgraph. Yes, it has been extracted. So the choice here has been this purple color, and then I have chosen the blue color, then I have chosen the black color, then I have chosen the brick red color. Is it all right? So I shall just define a traversal sequence in this sequence. Okay, what I tell that, if I see the front as a blue color, then the back of that will be yellow color. If I choose the front as the blue color, the back of that will be yellow color. If I take the next cube, then the front will become yellow color, back will become green color. Then they move in the direction of the arrow itself. In the third cube, it will be, front will be green color, back will be red color. Move in the same direction, front will be red color, back will be blue color. So this is what is the north-south alignment. Right? Did you get it? See, if this is the blue color, this is the blue color, the back of it is yellow color. The back of it is yellow color. So here, next comes this. This is the yellow color is the front, then the green color is the back. Yellow color is the front, green color is the back. Is it all right? Then comes this. So green color is the front, red is the back. Green color is the front, red is the back. Then you see here, red is the front, blue is the back. Is it all right? So it is possible. So I thought it is an exhaustive search algorithm, but graph theoretic modeling, and just manipulation of the matrices. In fact, I have shown it as a manipulation of diagrams here. It is not manipulation of diagram, it is a manipulation of your data structure, will immediately reveal that there is a set of two sets of walls. Two walls have been defined, have been shown to be composed of four different colors. It is a stack of four different colors. Is that all right? Now I have to remove this subgraph from this graph because I have already decided the north-south wall. Since I have decided the north-south wall, I should remove this. Remove what? Remove this graph. Well, remove this graph. That is what is. This is a small graph G. This is a big graph G. So it has got to be G minus G. So you do ring sum operation. G ring sum G. So vertices will not be lost. Only edges will be lost. Is that okay? All right. So you remove that. So you remove that. Could you get it? So that gives another resultant graph, isn't it? Reduced graph. This is a reduced graph. Now I have got to work out left face and the right face, left wall and the right wall. Again, my condition is I want to have four different colors. Therefore, again I should be able to construct one graph which is similar to this graph. What is that? It should have all the four vertices and it should be made up of four edges, and the four edges should be from four different cubes, If I can do that, other two walls, left wall and right wall, that is east wall and the west wall, also will be composed of four colors. Is it okay? All right. So can we see that? Is it possible? Yes, surely it is possible. You can see that you can choose the black. There is no other option at all. You have got to choose only black here. You have got to choose only brick red here. You have got to choose only blue here. There is no other option. And here, luckily, the option that this gets automatically eliminated because you have chosen that here. Therefore, the purple is left. And luckily, a cycle is available. A circuit is available. A subgraph is available. Good. A subgraph is available. Is that all right? Again, choose any direction of movement clockwise or anti-clockwise, but stick on to that. And therefore, east-west wall is also possible. East-west wall is also possible. Is it okay? So all four faces are made up of four different colors. Now there are very interesting questions. Question number one. Why these self loops were not considered while constructing these subgraphs? Right? I'm not going to ask these questions. Maybe when you get this assignment, your TS, our PhD, scholars would be asking you this question because you have got to answer this. Why these self loops were not considered? Now, on the contrary, I might ask a different question. I want at least one wall to be fully made up of one color. In other words, one wall should be fully red, or should be fully green, or should be fully blue. Is it possible? If so, what should be the type of subgraph that I choose? All right. There are four colors. Surely there are four colors. But I want to choose such a subgraph such that one wall is made up of only one color. It is fully blue, or it is fully red or green or yellow. All right. Can that be possible? At least one wall should be fully one color, or at least one wall should be made up of only two colors. Okay. So now the wall is made up of four colors. So what should be the condition if one wall has got to be made up of only two colors? What should be the condition if one wall has got to be made up of only two colors or one color, single color? How many such walls can be possible? So these are all the problems. Now let us try to generalize. Suppose I give 5 cubes and 5 colors. 5 cubes made up of 5 colors. Can I stack the cube one above the other such that all 5 colors are visible on every wall? 5 cubes with 5 colors. 6 cubes with 6 colors. So generalize n cubes with n colors. Then if you imagine n cubes with n colors and then try to solve it as a permutation combination problem, then you see how exhaustive search would have the problem would have become. It would have become a very exhaustive search problem. But graph theory conveniently solves the problem, and it is modeling a problem very thoroughly, and you have got to give the reasons. See, every such reason becomes a theorem of solving the problem. All right. So that is what is the way you have got to solve the problem. All right. But then I took it up. I purposefully took it up because I wanted to relate the connected and disconnected graph, and I wanted to relate this union, intersection, ring sum, and graph removal operations. I wanted to show. I wanted to illustrate that. That's the reason I took it. But in this cycle, definitely I shall not give a explicit problem on this. However, I shall give all the problems which are implicit, which are implied on this. So